for the invitation. It's a great pleasure. Okay, let me share the screen. Right. So indeed, I'll talk about cluster structure on Toda systems. And so in this talk, I'm not going to tell any new results. So this class structure, the phase space of the Toda systems was one of the first examples of, well, among the first examples of cluster varieties. So I'll be following some very classical works in this direction. In particular, it's goes back to Berenstein, Fomin, Zelevinsky, and Gekhtman, Shapiro, Vainshtein, and Fock and Goncharov. All right. So I don't really have much of agenda today. So please feel free to interrupt me and ask questions at any time. All right. So first, let me just focus on what is known as Cockster Toda system, at least in my understanding of this word. All right. So let's fix G to be a Lie group. It will be a complex Lie group. Well, the standard notation, so B plus and minus will be a pair of opposite Borels. H will be a maximal torus, so H will just intersection of B plus and B minus, so this is maximal torus. Let me kind of have a running example over here. So we can choose G to be GLN or PGLN or SLN or any other group of Dynkin type, but I'll be mostly referring to these two, and it will be convenient to kind of iterate for me between PGL and SLN. I'll do that. Some formulas are easier in PGL and some are easier in SLN. Right, then, well, obviously B plus is just the upper triangular matrices. B minus will be the lower triangular matrices. H will be diagonal matrices. Right. Well, and then I'll need notations for the Lie algebras. So G is the Lie algebra of G. B plus minus is the Lie algebra of this corresponding Borels, and H will be the Lie algebra of the maximal torus. So the Cartan. All right. Now, since we have a killing form on G, all right, so let this form here be the killing form. What it does for us in particular, it identifies say B minus, the negative Borel, with the dual to the B plus. Right? And therefore we can choose xi, just some basis in B plus, and then xi dual, xi uppercase, a dual basis. Sorry, xi will be a basis in B plus. Xi dual in B minus will be the dual basis. And then we can consider this element sum over all I xi wedge xi. So it's an element inside B plus wedge B minus. Or of course we can think of it as an element in G wedge G, and this is what is called the standard R matrix, right? So I'll call it R. This is the standard R matrix. So this element is of course doesn't depend on our choice of a basis. It's the canonical element, and the one way to think about it is kind of just identity. It's an identity homomorphism from B plus to B plus, just written in terms of B plus and B minus dual, right? So now, as we just saw, the R is as an element in G with G, it's a bivector to our group G at identity. And well, since we're going to talk about integrable systems, it means that their phase spaces are some Poisson manifolds. So I want to put a Poisson structure on G. And the so-called standard Poisson structure is given by a bivector field. So we need to take this bivector identity and create a bivector field on the group. And what we do is, so we just try the standard notation to explain it. So it's, we do the right shifts of the R matrix minus the left shifts, right? So it's right shift minus.
Take my good Apple plug.
Sorry? So it's right shift minus left shift of R, right? And this is a bivector. This is a bivector field. So in other words, when I say that it's right shift minus left shifts, I just mean that you know, pi at an element G of the group is, well, this R matrix to which we acted by G tensor G on the right minus you know, when we acted on the left. But of course I need to now, well, I'll say I need to induce the action on the vector field, right? And what happens if I do that? Well, G end out with this pi, it becomes a Poisson manifold, obviously. But moreover, it becomes a Poissonly group. Moreover, it is a Poissonly group. With the so-called standard Poisson structure, which is also sometimes referred to as Sklenin R matrix structure, the standard Poisson structure. Right. Now, well, if we have a Poisson manifold, we can ask what are the symplectic leaves of the Poisson manifold, and I'm doing that just because the Toda system effectively lives on symplectic leaves, or like almost on the symplectic leaves of this Poissonly group. So to describe symplectic leaves, we need a little bit more. So we need to know combinatorics of the Weil group. So let me just remind that Weil group is just a normalizer of the torus modulo the torus. So this is a normalizer of the torus. Well, of course, in type A, in our example, so if yeah, W is just isomorphic to the symmetric group on n-generators in Dynkin type AN. And then again, it's kind of some approximation to what symplectic leaves are the so-called double Bruhat cells that are in this story are even more important than the symplectic leaves themselves. So double Bruhat cells. These guys denoted GUV, and they are by definition elements of, well, sub-manifold from B plus U B plus intersect B minus V B minus, where U and V are two elements of the Weil group. So of course, when I write that, I use notation, and really what I mean, you take U and V elements of the Weil group, you take their representatives in the normalizer of the torus, so they lie in the group, and then you can form these guys, right? And they are, so these are Poisson submanifolds. And moreover, these Poisson submanifolds can all look the same in the following way. So this GV really just isomorphic to HUV, so it's some torus times symplectic leaves. So this is some torus, not maximal, some torus, and this is symplectic leaf. So in other words, you have symplectic leaf, and then you have this torus direction along which your Poisson bivector is just trivial, right? So if I wanted to draw a picture, I draw something like GV is just this, you have this symplectic leaf SUV, and then you have this torus direction.
Sash, could you comment an example of this Bruhat cell for two longest element of the Weil group?
Yes, absolutely.
Is it the group itself?
No, it's almost it's the group, but then you have to ask that some elements are invertible.
And I'll give
in the
group they are invertible in the group.
No. In the group, you just ask that the determinant is invertible. But in the biggest double Bruhat cell, you'll have the principal minors and kind of the opposite of the principal minors are invertible, right? So indeed, yeah, it's a good question. So example. So
if it's not difficult, just to.
I'll give this example for W naught, and then I'll actually give a parametrization of double Bruhat cells from which it will be clear which things are invertible. But let's just do indeed this example. So if both of them are the longest element, then this G W naught W naught, this is well, these are elements of G in G. Well, in G, let's say let's say SLN, right? Let's do SLN. So G and SLN, such that the well, kind of the principal and the sort of opposite principal minors are invertible. And let me just draw them. Opposite principal minors are invertible. And that just means that, if I have a matrix, this is my element in SLN, I ask that these guys are invertible. So this element, and then this minor, and then this minor, and then this minor, and so on. And then on the other hand, I ask that this minor, and this minor, and this minor, and this minor, and so on are invertible. Right?
Thank you.
Good. Perfect. Cool. Right. So these are Poisson submanifolds. Good. Now, well, if we want an integrable system, we'd like to know, well, obviously dimensions of the Poisson submanifolds, because we're going to compare in dimension with the number of Hamiltonians we have. So I haven't described Hamiltonians yet, but I will in a second. But just for now, let's discuss dimensions. So dimension of this GUV, it's not too hard of a calculation. It's actually length of U plus length of V plus rank of our Lie algebra. So this is the dimension. And we also have functions in involution, and those will be, so I just need to take trace in the ith fundamental representation. So I will denote it this way, trace of omega I. So the trace subscript omega I, this is the trace of an element, trace of an element G in G in the ith fundamental representation, right? So this is a function on our group. And the claim is that these trace omega I are in involution. And yeah, well, it's clear how many of those we have, right? We have, rank many of those. So trace omega 1, trace omega rank G are in involution. Well, the reason I chose, so clearly what I've just done, I've just figured, I just chose a basis in the algebra of symmetric functions of eigenvalues of my matrix of SLN, right? Because trace is just some of those, and trace omega 2, trace omega 1 is just the trace omega 2 is the first elementary symmetric function. I could have chosen any other basis in the algebra of symmetric functions of eigenvalues, but these will be directly related to Toda Hamiltonians. So I chose those. All right. Now, we're almost good, except for, well, really the phase space of Toda system is slightly different than what I just described. And the phase space is really the reduced double Bruhat cell. And when I say reduced, it just means that you take GUV and you mod out by the conjugation action of the torus. So I write a joint H, which is of course a abuse notation again, but just means I conjugate by the torus. So this is the so-called reduced double Bruhat cell. And if torus acts freely, which it almost always does, at least if your U and V are large enough, then you have. Sorry. Take it back. Torus always. Give me a second to think. Yeah. Okay. Maybe torus. Yeah, torus doesn't always act freely, but if U and V are large enough, then it does. So in particular, if we take. Yeah. Okay. Let me just try this. So if yeah, add h x freely. Then dimension of this reduced double Bruhat is length of u plus length of v. Right. Hi, Gonya. I'm amazed that you still came after our conversation yesterday. All right. Good. Now there is so I mentioned that I'm going to discuss the Cockster Toda system, right? So Cockster elements should appear, and here what Cockster elements are. So an element C in the while group is a Cockster element. If it can be written in the following way. So clearly any element of the while group I can write as just a product of elementary letters or elementary transpositions. And if I can write C as Si1 ... Si rank G, such that each transposition appears exactly once, each elementary transposition appears once. Then that's what's called the Cockster element, right? Now, if C and C prime are pair of Cockster elements, so if both of them are Cockster elements, then dimension of this reduced double Bruhat G C C prime mod at H is equal to, well, length of one plus length of another, which is just twice the rank G, and we get an integrable system. So we get an integrable system, and this is what is called Cockster Toda integrable system. Integrable. Now, maybe I should make a remark here that of course you can play the same game on other double Bruhat, and when you do it with the arbitrary u and v, you get what people call generalized integrable system. Generalized Toda systems. And Reshetikhin showed that these are degenerately integrable, meaning that you don't have enough Hamiltonians, but you have Hamiltonians plus you have this huge subalgebra functions that commutes with the Hamiltonians, but is not commutative, but somehow is not commutative itself, right? So I won't say anything more about that story for now, but if there's any interest, we can discuss maybe after the talk what this clusters that I'm going to describe now, what they have to tell about this degenerately integrable system, because what they really can tell you is they can show you that those generalized Toda systems are actually completely integrable, but that's a separate story. All right. So this was the description of the integrable system. Now I'm going to describe the cluster coordinates on.
Sasha, I'm sorry. Are you sure that it is not integrable in an ordinary sense?
Well, that's what I said. So the known result about generalized Toda systems,
yes,
the written one by Reshetikhin, right, is that they're degenerately integrable.
So if you know what is called the constant full Toda system, it is completely integrable in the Liouville sense, but it is also integrable in generalized non-commutative sense. So it is both.
That's right. Yeah, but I'm saying that for.
Okay. We can discuss it later. But about your definition, is the Cockster Toda system in some particular case is just an open Toda chain?
Yeah. That's precisely there. The Cockster Toda is precisely an open Toda chain.
Okay. Thank you.
Yeah. Now, right. So just to the last comment on what you said is that indeed. So the result on Toda, on general Toda system that I know is that they're degenerately integrable, but also what I'm claiming is that if you look at clusters, you can also show that they're completely integrable as well. There are two independent statements, no one follows from the other, but both are true. All right. Now, so the second part, that I wanted to discuss of this talk is just cluster coordinates, and really, or sometimes people call it cluster structure on the system. So what I will be doing, I will be constructing some very nice set of coordinates on double Bruhat cells and reduced double Bruhat cells, and they will be nice from the Poisson geometric point of view, but also we'll see that they're actually useful in other sense as well. And I will not just describe one coordinate chart, but rather I'll describe infinitely many coordinate charts in general, and they will glue into a variety, those coordinate charts, that then this variety kind of defined completely independent of our double Bruhat cells will actually coincide with our double Bruhat cells. So that will be one of the results that I want to describe. Now, let me again focus on, so for now, let me focus on G being equal to PGLN. Everything I'm going to say now, of course, generalizes to other types and has been generalized. And I will be following, as I said, all these works I mentioned before, but let me maybe just to, well, create rather than avoid some confusion, let me put some terminology. So the type of, so there are two types of cluster coordinates. And what I will be describing is what Gekhtman, Shapiro, and Vainshtein, well, maybe let me put names, Gekhtman, Shapiro, Vainshtein, call those coordinates that I'm going to describe y variables as opposed to x variables. And what Fock and Goncharov call x variables as opposed to a variables. So as you can see, there's a huge deal of confusion every time people say, x, y, or a, and so on. So there are two ways to avoid this confusion. So one way is to just call them cluster Poisson variables. So whenever you say that, that's unambiguous, cluster Poisson variables. But since the other set of variables won't appear, I will just call them cluster variables. That's it. So if you know this literature, then just refer to, well, here's the dictionary. Right now, so what I'll be doing, I'll just consider a parametrization of double Bruhat cells. So here's some parametrization, and this parametrization will actually explain exactly what what elements are invertible or what are not. So parametrization of GUV as follows. To parameterize that, I'll need to choose how I want to write words U and V in terms of elementary transpositions. And I'll write V as SI1 ... SI K. And I write U as SJ1 SJL, but I will need to distinguish between the two. So I'll put bars over here, just meaning that, so these are the very same letters and the very same while group, but just, so I just want to consider two separate while groups. Two identical while groups, but separate, two different alphabets. And now I will, to parameterize the element of the double Bruhat cell, I'll need to introduce some matrices. So HI of X, just by definition, will be this matrix. So it will have first I and diagonal matrix. First I entries are X's and the next are ones. So I have I entries here and n minus I entries here. EI will be this matrix where I have this block, this block 1, 1, 0, 1, and then just diagonal matrix with ones. And this element here is on the ith row, and then Fi will be EI transposed. And then I choose a shuffle. So choose a shuffle I of this word VU. So what does it mean? Let's do an example. For example, say V is PGL3. Say V is S1, S2, and U is S2 bar, S1 bar. And then I can choose a shuffle I to be this S1, S2 bar, S1 bar, S2, right? So I cannot change the order of letters in U and V, but I can shuffle one letter through the other. And then as I choose a shuffle, I construct a a map, let's call it tau I. So it will be a map from C star, in our case, 6, to this double Bruhat cell G, U, V. And here's how this map goes. I just have this 6 coordinates here, x1 up to x6. Obviously, it's C star, so all of them are invertible. And what I do, I write the following thing. I write, let me just write expression, and then I'll explain why I've written this way. So h1 of x1, h2 of x2, e1, h1 of x3, f2, h2 of x4, f1, h1 of x5, e1, e2, h2 of x6. So what's really written here is the following, right? So this, this here is just a torus in PGL3. This corresponds to letter S1. This corresponds to letter S2 bar. This corresponds to letter S1 bar, and this corresponds to letter S2. Right. Alternatively, of course, I could have written it also this other way. Let me also I just want to show that there's there's some asymmetry here because I put torus on the left rather than putting torus on the right, but that's really not a problem at all. I can do that as well, just putting h1 of x1 e1, h2 of x2 f2, h1 of x3 f1, h2 of x4 e2, h1 of x5, h2 of x6, and now we see that now this is torus, and we can treat this one as kind of our what we assigned to S1. This is what we assigned. This is S2 bar. This is S1 bar, and this is S2. Right. So here I literally done nothing. I just commuted matrices one through another that commute. Right. So HI commutes with EJ and FJ as long as I not equal to J. So this is the reason why these matrices are chosen kind of to be labeled by weights rather than roots of our linking diagram. Good. Now, fine. So this is the parametrization, and if you spell it out, you can see from this parametrization, since all of x1, x6 are invertible, you can see what elements have to be invertible. Now, let's actually draw these matrices, so that will be extremely helpful to draw them. So let's try to draw. So what is h1 of x1? Well, this is this matrix x1, 1, 1, and I want to draw that as just this what people call network. So I'll draw these 3 strands, and I'll put x1 between the first and the second. And the way to see this, so the way to see why this network represents this matrix is the following. So if I have a network, the matrix Mij that I construct from a network, the matrix M, so ij runs from 1 to n, that I construct from a network is the following. So the entry Mij is just sum over all paths in the network from I to j, weight of the path. So weight of the path is this guy here. Weight is the product of all xi below the path. So in our case, the network is extremely simple, almost trivial. So we have unique path from I to I for each I and nothing else. And from 3 to 3, there is no axis below that. So we put 1. From 2 to 2, there are no axis below. So we put 1. And for 1 to 1, there's one x1, we put x1. Right. So then we obviously we can tell what happens if we do H2 of x2, right? So this is x2, x2, 1, right? But also it's represented by this network, again, 1, 2, 3, 1, 2, 3. And we just put x2 over here, right? So now below 3 to 3 is 1 because there's nothing below, but for 2 and 2 and 1 to 1, there's x2. And we obviously can write E1. So let me just remind that it's this guy here. And what's the network? It's just this guy here. And I don't put any weights, right? Because now what I have a path from so along with paths from I to I also have a path from 1 to 2, and that's exactly this entry over here. Good. Now, what's our network? So what's our network for this decomposition? So we have indeed. Let me remind. So we have this word I. Sorry, this word I, which was S1, S2 bar, S1 bar, S2, and really we can just represent it by this network. Like this, and so S1 means that we have one strand going vertically down there. S2 bar means that we have, so bar versus non-bar, just it's a direction of which way we go, which way the vertical arrow points. S1 bar is here, S2 is here, and then we put our variables. So it's x1, x3, x5, x2, x4, x6. And this is, so this network just represents this decomposition, or this one, that's the same. All right. Well, obviously, when you multiply matrices, you just concatenate networks. Now, the non-trivial claim and the first manifestation that cluster variables are actually interesting objects is the following. So remember, we at the very beginning, I explained what the Poisson structure on the group is. And we discussed whether the Poisson submanifolds are there. But when you restrict, obviously, you get some very non-trivial Poisson brackets if you just write it in terms of matrix elements of the matrices you look at in SLN, right? And the claim is that the Poisson bracket is a log canonical in these variables x1, x, well, in this case 6, in general, of course, x1, well, the x dimension of our double Bruhat cell. And log canonical just means that if you take Poisson bracket of, sorry, maybe I should, yeah, I mean, just variables here. The Poisson bracket of xi and xj is epsilon ij, xi xj, where epsilon ij is just a constant. All right, so this guy here is a constant. Now, how do we write out these constants? And here's how you do that. It's again just completely combinatorial procedure. So I'll do some combinatorial, some very superficial stuff. Don't pay attention to it. So I'll just put black, and instead of arrows, I'll put black and white vertices. It helps. So the point of each arrow, I'll put a white vertex. And instead of the source of each arrow, I put a black vertex. So now we have a bipartite graph. Well, sorry, black-white graph, not bipartite. And then what I want to have, so what I have? I have these cluster variables, these x's, they correspond to vertices of the dual graph.
Sasha, I'm sorry,
yeah.
I missed something. Are you talking about what Poisson structure are you talking?
So we took the standard Poisson structure, this Kleininar matrix, standard Poisson structure on the group G.
Yes.
Double Bruhat cell is its Poisson submanifold. And I'm claiming that you can find coordinates in which this Poisson structure is log canonical.
But are these parameters are coordinates on the Bruhat cell?
Yes, absolutely. Yeah, they are coordinates. Yes. Yeah. The coordinate chart doesn't cover the whole Bruhat cell, but they're coordinates on the Bruhat cell, right? I'm just saying that I can find coordinates in which I can find coordinates in which the Poisson bracket becomes log canonical. Right? It's not log canonical in matrix coefficient. Well, matrix coefficients would be another obvious choice for coordinates, right? But Poisson bracket in terms of matrix coefficients is complicated. In terms of these coordinates, it's very simple. And now I'm just describing a recipe on how to see. So we already know kind of the general form of how this Poisson bracket should look like, right? It's just the Poisson bracket of two coordinates is constant times their product. But now I'm just trying to explain combinatorics that will tell you how to write these constants out, right?
They are coordinates on a dense subset, right?
Precisely, yes. They're coordinates on a dense subset. Yes, exactly.
And then you have various shuffles, and they give you the whole cluster algebra structure.
Yes, that is true, but I'll come back to that. So that is true in this case, but in general, it's slightly more complicated. Yeah, good, right. So now, how do we write brackets? So how do we figure out this constant epsilon ij? I will now just draw a dual quiver, but I want to direct the arrows, the edges of the dual quiver, and the way I will direct them. So well. If I have a black-white edge of the original diagram, I'll draw an edge of a dual quiver. Oh, sorry, an edge of a dual quiver, and I'll direct it in such a way that the white vertex stays on the right. So I have an arrow from x1 to x3. I have an arrow from x5 to x3. I have an arrow from x3 to x4. I don't have an arrow from x2 to x3. Because this edge is not black-white, and similarly, this one is not black-white. I'll have these two arrows, and also I'll have the following. So kind of, you see, I have black-white. I have black versus white versus, and I have terminal vertices here. And whenever I have a terminal vertex, I'll also draw an edge so that white stays on the right and black stays on the left. But I'll draw a dashed arrow here. So I'll draw a dashed arrow like this, and a dashed arrow like this. And I'll explain what these dashed arrows mean. So then the rule is simple. So epsilon ij is just number of arrows from I to j minus, from arrows I to j minus number of arrows from j to I. And dashed arrow is just 1/2, this is just the notation for 1/2 of the solid arrow. So in other words, epsilon 3,4 is equal to 1. Therefore, the Poisson bracket of x3 and x4 is just x3, x4. And epsilon 1, 2 is equal to, well, arrow goes from 2 to 1, right? And it's dashed, so it's minus 1/2, and therefore x1, x2 is minus 1/2 x1, x2. Right. So this is just some cluster, some coordinate, it's coordinates on a dense subset of the double Bruhat, and this dense subset is in this case c star to power 6, in general c star to some other power. All right. Now, what happens if we reshuffle I? So now question: what happens if we reshuffle I, or in fact, what other things that we do? Remember, so when I was even defining these words u and v, I chose some decomposition of these words in terms of elementary transpositions, so I can as well do this braid move si plus 1 si, exchange it with si plus 1 si plus 1, and have the same element of the while group but different writing. And let me so the same thing will happen in both cases, but let me just focus, since we have this running example of a double Cockster word where we don't have we cannot apply this move. Every letter appears just once. So let me just show how you reshuffle things. So example, gonna answer this question by showing one example. So if we write s1, s2 bar, s1 bar, s2, well, you can see that in all constructions that I've just outlined, this word is just identical. So this is just an equality with the word s2 bar s1, s1 bar s2. this is just saying that that E1 commutes with F2, and H1 commutes with, you know, HI commutes with EJ if I and J are not equal. So these two words I can just shuffle through another without any problem. Nothing will, parametrization will not change, coordinates will not change, nothing. But then I can do the following thing. I can shuffle S1 bar through S1. And here I will get an honestly different picture. So let's draw the corresponding picture. So I'll have now black-white graph like this. So as opposed to, so the first thing that happened is what happened from here to here, I shuffled this edge over here, right? And then I had vertices white, black, and here I just changed them to black, white, right? So I just changed colors of one square face. And I can write variables here, x. So and then I can write the same. We'll try to write the same element of the element of the double Bruhat cell. So I'll have some new coordinates: x1 prime, x3 prime, x5 prime, x2 prime, x4 prime, x6 prime. And I can try to compare the two, right? So originally I had an expression. Let's see where it is. I had an expression like this. And now I have an expression, well, yeah, h1 of x1 prime, h2 of x2 prime, well, f, actually, yeah, write it out. So f2, h2 of x4, f1, h1 of, sorry, not what I wanted to write. F2, right? F2, H2 of X4 prime, F1, H1 of X3 prime, E1, H1 of X5 prime, E2, H2 of X6 prime, right? Yes, good. So now I need to compare these two expressions, and well, first of all, to make them slightly, so yeah, to make them right. So this expression corresponds to this writing. This expression corresponds to this writing. Now, what corresponds to this writing? Well, as we discussed, I just need to kind of do the same thing. But here I just take, permute, I take this one out, just commute it through E1, H1, right? Now, let's look carefully at these two things that we want to compare now. Well, really, the only kind of place where they differ in a principal way is this place here, because I have E1, H1, F1, and here I have F1, H1, A1, right? And the question is, how do we, now we just want to solve this for new variables, for x1 prime up to x6 prime. In order to solve that, we really just need to kind of be able to write this expression in F1, H1, A1. And here's how it can be done. I'll just give you the end result. Hopefully you'll believe me. So if I write E1, H1 of X, F1, I get, well, I get some matrix, you know, in this example, like this. And if I wanted to write the same, but when F and E are reversed, then what I will have to do is the following. I will actually have to write H1 of X plus 1, F1, H1 of X inverse, E1, h1 of x plus 1 and then h2 of x over x plus 1. So what does it mean? It means that, well, I can indeed swap f and e, but at the cost of a changing what stands between them, and then having a bunch of additional h's, h1s and h2s, right? So what will then happen? This h2 can be factored inside h2 of x4 prime. And these h1 and these h1 can be factored into this h1 of x5 prime and this h1 of x1 prime. Right? So in other words, what we get is that new variables, so x3 prime is just 1 over x, x1 prime is x1 times, 1 over x3, x1 is 1, x1 times 1 plus x3, x5 prime is x5 times 1 plus x3, and x4 prime is x1 x3 over 1 plus x3. Let me now draw the same thing, but in terms of quivers that tell us the Poisson brackets. So before we had a quiver, I have it somewhere probably, maybe I don't, okay, let me just draw it. So before we had a quiver, originally we had a quiver like this. And this was x1, x3, x5, x2, x4, x6. And now we got a quiver like this. So it goes here, and this goes here, and this goes here. This goes here, this goes here. Oh, sorry. So this is x1 prime, x3 prime, x5 prime, x2 prime, x4 prime, x6 prime. And to go from one to another, you see, we were looking at this one spot over here. So there was exactly one h that was standing between e and f. So there was this one single variable x3, which kind of told us, at least combinatorially, what do we do? Like what we have to refactor. And we will denote this thing mu3 because, well, 3 just tells us that it happened at the variable x3. Right? So in other words, it happened at this spot of our, yeah, invisible. At this spot over here of our graph, of our cluster quiver, so to say. Now, it's kind of from the shape of the quivers and what happens. It's you can probably already guess what the general form of cluster transformations. But before I do that, let me actually just finish the story about clusters and Toda Hamiltonians, and then I will come back to cluster varieties. Right. So what do we have then? So we know that each double wild word. Each shuffle of, I guess I have to say each shuffle of a double wild word gives us a chart with denoted x or chi I for shuffle. This is isomorphic to C star to the dimension. And then we have these charts mapping to GUV, but also some mutations between the charts. So this is called a cluster mutation over here. So this is cluster mutation. Now this maps between the charts. So this is chi prime. This is mutations mean. So we have this weird thing that as soon as we found one chart, we can now construct new charts just from the data of the first one. So we found one chart, and then we can mutate at this spot, or mutate at this spot, or mutate at this spot. So we found one chart, and then somehow miraculously a whole variety pops up. So we have these charts, and we treat mutations as the gluing data, right? So these mutations is just gluing data. between charts. And as Alexei mentioned earlier, indeed, if as soon as I found this one cluster chart on the double Bruhat cell, I can just start cooking up other charts and gluing them together. And at the end of the day, I will glue back the whole double Bruhat cell. And this is saying that, and this is what means to be a cluster variety. So double Bruhat cell is a cluster variety labeled, well, and the charts are labeled by these quivers, and so cluster variety is labeled by the mutation class of the quivers. Okay, we'll come back to it in a second. Let's talk about what happens in a reduced cell.
Sasha, could you just comment if this parametrization and this mutation are related with Lustig parametrization, for example, but it is not your case, so it's different double Bruhat cell. So, for example, for the identity element in the while group and the longest element, you obtain the upper triangular subgroup, and you obtain. Is this parametrization work in this case, and is it related to the Lustig parametrization and Lustig mutation?
It is related. It works for any double Bruhat cell, and in a way more general setup. It is related to Lustig parametrization. In fact, Lustig coordinates will be there's a monomial transformation that transforms one coordinates to another. You can rewrite cluster mutations in terms of Lustig transformations.
I suppose, but these are exhaustive, a little bit exhaustive in the generic cell. Am I right?
Say it again.
It is exhaustive. There is some reduction. Am I right?
Sorry, what is exhaustive?
Just that the number of coordinates is bigger than the dimension.
No, number of coordinates is number of coordinates is precisely the dimension always.
In generic Bruhat cell.
So right, so but you see the dimension of the generic Bruhat cell is lambda v plus lambda v plus rank. And what I've done, I put the torus, which gave me the rank, and then one coordinate for each letter. So so number of coordinates is precisely the dimension.
Okay.
Yeah, and it is related to Lustig's parametrization, but there's a monomial transformation between those. So, okay, now reduced cell. Reduced cells. Well, so what is a reduced cell? I just need to mod out by the joint action of the torus, and again, let's just look at this quiver. And when I act by the torus, by joint action of the torus, well, remember these. So really, all these coordinates, they kind of stand in, these coordinates, they stay here, and the others stay here. When I multiply by the torus on the left, I just scale these two, and multiply on the right, I just scale these two. So when I do a joint action of the torus, the only thing that happens is, well, this one multiplied by T1, this one multiplied by T2, and this one is divided by T1, and this one is divided by T2. Right? So this is this is how the torus acts. So this is a joint action of the torus. Yeah, over here. Now, if I wanted to mod out by this joint action, well, I just need to take invariants, and so this add H invariants, and H invariants are generated by well x1, x5. Because I have to take product to kill the T1, x2, x6, x3, and x4 because T just doesn't act on those. And when we do that, well, really, we just get, what's x1, x5? It's just a product of those. And now I can draw a new quiver, how the product commutes with everything else. Because quiver, after all, just tells me the commutation rate, the Poisson relations between the coordinates. So what I need to do, I just need to glue those two variables. When I do that, I get a quiver like this.
Excuse me, maybe I also has with respect to Dmitry question. So if we just have Lustig parametrization, then we have chamber ansatz, and there is a twist involved in this. So if we just go to coordinates, and in your case, the chamber ansatz would be just exactly y coordinates. It would be no any twist.
I forget
or they exist.
I forget a little what the chamber ansatz is.
The chamber ansatz is just expression. So if we consider Lustig parametrization, then it's expression of this parameter Ti in a cluster variable or in X cluster variable.
Yeah, right.
and then, but it's not direct, so it's also use twist. So because for
yeah,
example,
if
you are in GE double zero, then you just go to opposite. And in your case, so it would be not twist, or
no, I think that
it would be hidden somewhere.
I think there's still a twist, but there's just another complex, because I think
because formally it seems that in your case chamber ansatz just exactly these parameters. They are
right. But here there are kind of three ways to choose coordinates, right? There's the A coordinates, the well. In
but in your case,
blue stick, and all of them are related by some monomial transformations. So I'm not prepared to comment now on. So I think twist is, as far as I remember, twist is still here, but I'm not prepared to give a more detailed explanation right away. I'll have to look it up. But I'll be happy to discuss after.
Okay.
Yes, sorry.
Thank you.
Yeah, absolutely. Sorry. Right. So let me now call this variable somehow. So this is y1, y2, y3, y4. And what are those? So this is y. I guess this is y2. This is y3. This is y1, and this is y4. Right. Okay. So I get this clever now. Now, remember I promised Toda Hamiltonians. So. By the way, Dima, how much time do I have? When I have to finish?
Half an hour, but
okay.
I have a dream to continue your talk after.
Okay, yeah, absolutely. Okay,
one of the next times.
Okay, great. Okay, so Toda Hamiltonians. Well, okay, so what were those? Really, we wanted to remember how we had this. Yeah, we wanted to say that these traces in fundamental representations are some Hamiltonians, and let's see how this works. So there will be a difference between PGLN and SLN case. So I'll do both. Now let's just see how we can calculate traces. Sorry. So we'll be calculating them in this original cluster. Right. So let me call this HI hat. This will be an I tuple of well, sorry, rather weight of an I tuple of non-intersecting paths, of non-intersecting paths, and then I sum over all tuples. So let me just give an example of how it works. So let's see what's H1 hat. Well, H1 hat is just the sum over all possible paths from 3 to 3 and 2 to 2 and 1 to 1. Right. So this is literally the trace. Now, what do we have? Well, first of all, 3 to 3. There's this path, and there's this path. Oh, sorry. There's this path. Right. So there are two of those. So I get 1 plus x4. Then for 2 to 2, there's just one way to go. So this is x2, x4, x6. And for 1 to 1, there's this path, and there's this path. So the top one just has product of all the variables, and the bottom one all but x3. So I have x1, x2, x4, x5, x6 plus x1 dot x6. And now if I want to rewrite it in terms of y variables, well, I get one. Well, sorry, in terms of variables that I called y without any variables that we called y here. You see how all of these guys, they depend on the product. They don't depend separately on x1 and x5, but they depend on the products x1, x5, and the same for x2, x6. So this will just become 1 plus y4 plus y3, y4 plus y2, y3, y4 plus y1, y2, y3, y4. And you can notice that it's kind of this telescopic sum that actually has a very precise meaning. But again, let me just mention that it is there, and we can discuss it later. We can do the same for H2 hat. And again, so what's H2 hat, right? It's the product of all two tuples of path. Well, okay. So if one of our path is 3, right? So, well, if you take path 3 with path 2, there's just one way to make them non-intersecting. This is just the path 2, right? So that will give us y3, y4. Now, 3 can also go with the path 1, right? So that gives us y1, y2, y. Well, sorry, 3 can go with the both ways how 1 can go, like this and like this, right? So it gives us just the weight again of the path 1. So it gives us y2, y3, y4 plus y1, y2, y3, y4. Then there is a pair 3. Then there's a pair this 3 and this 1, right? So it gives us just extra x4. So it gives us y1, y2, y3, y4 squared. And finally, path 2 and path 1, there's just one way to make this non-tuple non-intersecting. So we get y1, y2, y3 squared, y4 squared. And the last one, h3 hat, is just a product of all 3 paths. This is y1, y2, y3 squared, y4 squared. And you can see that this guy is actually a Casimir, simply because product of all these guys is a Casimir and product of all these guys is a Casimir. So this is also a Casimir. And finally, I just define hi to be hi hat divided by h n hat, in this case n is equal to 3, to power I over n. So this is kind of the SLN versus PGLN case, right? So I just divided by the nth root of the determinant. So in particular, h1 becomes h1 hat divided by y1 to 1/3, y2 to 1/3, y3 to 2/3, y4 to 2/3. h2 becomes h2 hat divided by y1 to 2/3, y2 to 2/3, y3 to 4/3, y4 to 4/3, and h3 is just identity. It's just 1. So this is SLN story. All right.
Sash, could you comment how this construction is related to some invariant construction, for example, from Berenstein and Schrader, which comes from something like like k invariant function on G over k?
Yes. So in all of these cases, what relates, what's common for all the Toda systems is that the Hamiltonians are effectively always just traces of some matrices. Now the phase spaces are constructed in somewhat different ways. So really, for example, what you can do if you talk about Cockster Toda system, you can take 2 Cockster words, for example, like what we had. And if you really look at what is our, if you take these 2 Cockster words as S1, S2, and S2 bar, S1 bar, you will be looking in PGL3 at matrices like this.
But is it right?
It's really tridiagonal matrices with some.
Is it right that it is the same as k invariant function on G over k?
Almost. My story is complex, right? Their story is real, and I'll explain. And let me just finish the sentence. I think I'll give some answer. So we're looking at tridiagonal matrices, and you can do this. And what you can do, you can say, well, we can factor this tridiagonal matrices into, something like this: lower triangular, right, and upper triangular. And you can, obviously, you have to mod out by the torus that acts, that sits in the middle here, right? But what Gus and Collet did, right? They said, okay, fine, let's look at the real case, and let's take matrices. Let's take one matrix just the matrix with 2 diagonals, and take its transpose. So now it becomes symmetric, and then just take G times G transpose. So it gives us, this is G and this is G transpose for them. and then you get a tridiagonal matrix, and then you take a trace. But their story is a story about real manifolds, and this story is about complex manifolds. That's fine, but it's just so they just construct phase space of some real phase space of a system of this Cockster Toda system, and then take traces of the same matrices.
Yeah, but if we consider this is flows of size k like determinant, then it just becomes the sum of determinants, so some minors. So
sorry, could you say again?
H1 it would be just trace.
Yes.
So H2 it would be just a product of minors.
Yeah, absolutely. Product of 2 by 2 minors on diagonal.
Sum of minors.
Sum of 2 by 2 minors. Yes.
Yeah. Then sum of 3 by 3 and so on.
Yeah, absolutely. But that's the same as I said. It's the same as saying that it's trace in the fundamental representation. Yeah. It's just a way, again, it's just a way to choose basis in the algebra symmetric functions of eigenvalues of the elements.
This is just comment to Dmitry's question. So it's just invariants. So if you consider this, it's just sum of minors.
But it is right, for example, that it is somehow related to B invariant functions on G.
I don't know.
In full Toda lattice, in full Toda system, it is the case. So
why B invariant functions?
It is a Adler-Kostman sim reduction over B.
Oh, you mean you take T star to G and then you mod out and you do control reduction with respect to n minus and n plus?
Yes.
Yes, absolutely. But I mean, well, morally, it's I mean, when you do that, you just consider tridiagonal matrices, right? When you do that.
Yes.
So, and this is just another way to construct tridiagonal matrices, except for in this classical story, well, the story that was before Pashetnikov and Alexei, right? You would get tridiagonal matrices without, kind of in the algebra, and here you get tridiagonal matrices with some non-zero, well, additional conditions that some elements are non-zero, right?
Could you continue? It's a point for
okay, good,
for deep conversation. Okay,
right. So now I wanted to talk about quantization, but before that, let me just say one word about cluster varieties, or maybe I already said one word, but I want to put it in writing, and then discuss quantization. I think I'll be on time. So cluster varieties. Well, what do we really have, right? So Q is a quiver. And each quiver defines us a chart, which we can call chi q, which is isomorphic to C star to some power. And what we did before, we just said, well, if you have a shuffle of a double wild word, you can construct a quiver from it, like I showed, but you can just forget about double Bruhat cells and just start with arbitrary quiver, get a chart, and start mutating the chart, right? So also, what the quiver does for you defines Q. Well, Q naught is just, maybe let me just say vertices of Q. So just number of vertices of mutations, because you can take any vertex and mutate the quiver at this vertex, like what we're doing before. So you can do this Q prime, which is mutation of the quiver Q at vertex K. So this is mutation at vertex K. And I mean, sometimes it's very useful, and people use it all the time, that sometimes you need to prohibit to mutate some vertices. They're called frozen vertices. Then you just mutate everywhere but at those frozen, and they're frozen once and for all. But in general, you can just mutate it pretty much any vertex. Now, how does this work? Well, from the pictures we've seen, we know exactly kind of what combinatorial rule to expect. Let me just draw that once again. So let's say we start from a quiver like this. Now let's call this x1, x2, x3, and x4. And then we mutate at, let's say, vertex 3 again. And well, if you look carefully at how well, if you look at how the variables should change, well, the variable we mutate at, that just becomes x3 inverse. Now, if there was an arrow pointing to x3, then this becomes x1 times 1 plus x3. If x3 was pointing to something, this becomes x2 x3 over 1 plus x3. Right, but here we have this additional wrinkle that we also have kind of double arrow pointing to x3. That's not a problem. You just multiply by 1 plus x3 squared. So that becomes x4 times 1 plus x3 squared. And then just looking at that, you can just compute the Poisson brackets between those functions. And what happens is the quiver that you get, I'll just draw it for you. So it becomes the curve like this. And really, you can actually just tell the rule right away. So what happens with the quiver? So what happens really, just on the level of quivers, you take this vertex, the one you mutated at, and then you take all the arrows that are incident to this vertex and invert them. So we inverted these three, right? And then if you got an oriented triangle, if you got an incoming and outgoing arrow, you complete it to an oriented triangle. So here you had three things going this way and then one going the other way. So they cancel out, you get just a double arrow because you're only interested in the incidence matrix. And here you also complete it to an oriented triangle, so you get this double arrow. So that's what the mutation looks like. Now you can also see that if we just cross out this 1 plus x3, every instance of 1 plus x3, the quiver will be exactly like you see over here. And that's something that we'll see immediately from the quantization, why this 1 plus x3 doesn't really matter. But before that, let me just again point out that mutations are just gluing, so they give gluing data for cluster charts. And so what this really means, that just means that they give birational isomorphisms. Let's call them mu k between x q and x q prime. And birational means that, well, I need to localize both of those somewhere, right? Now, what I can do as well, and what people do often, and this is the only thing that's meaningful to do when we start talking about quantization, is instead of varieties, we start talking about algebras of functions in this variety. Okay, I just lied blatantly just now. Of course, you can do much fancier stuff. You can take what you should really be doing is taking a category of quasi-coherent sheaves and quantizing that. So I will not discuss that. I work purely, right now we only work on purely algebraic level. So I will be only quantizing the algebra of global functions on this variety. So you can take, we can set L to be a universally Laurent algebra. So what is the universal Laurent algebra? Well, what's global algebra of functions on a one torus? It's just Laurent polynomials in variables of this torus of C star, right? Of C star to them. Now, if you went from one torus to another, well, the global function would be something that looks as a Laurent polynomial in both charts. So universal Laurent algebra is the algebra consisting of those elements that are Laurent in every single chart, right? So this is just L is just the algebra of global functions on this variety. And of course, no one promised us that these functions even exist. I mean, if we don't know that some other fancy cluster variables exist, from what I've just explained, there's no guarantee that this algebra is non-trivial, but it always is, and and there are ways to write elements of this algebra. And then we can just take chi to be the spec of L, and this is affinization of a cluster variable. Affinization of the cluster variable. And basically, the claim that comes as in my setup comes as a combination of work of Gekhtman, Shapiro, Vainshtein, and Goncharov, and Berenstein, Fomin, Zelevinsky, but originally in some other setup was proved by Berenstein, Fomin, Zelevinsky, is that GUV, and I guess I should add guys like Gus Schrader as well, GUV and GUV mod H are cluster varieties. So they're affine and they're cluster varieties. And a subset of charts, a finite subset of charts, finite subset of charts is parametrized by double wildwords. But in general, there are infinitely many charts. by double Y words. In particular, you can see that they're way more charged than words because, well, so the quivers that I've been drawing, those quivers were just drawn on disk, and this quiver was drawn on a cylinder because I took something on a disk and glued and connected the right and left. But now if I take this quiver and mutated this vertex, right, then it will stop being planar, so it cannot correspond to any wild word. So there are infinitely many charts, way more than wild combinatorics, but yeah, and yeah, commenting on Alexei's comment from before, indeed, as far as I remember, in this case, it's enough to just take all possible wild words to cover the whole variety. Yeah, it's definitely true, right? But there are more charts. Fine. Okay, so unless there are questions about this part, let me switch to quantization, and yeah, I think if 10 minutes is enough for. Yeah. So yeah, okay, quantization, right?
Yeah, it's okay.
Good. Okay, so any cluster Poisson variety. So I write cluster Poisson because, as I mentioned before, there are two types of coordinates, and we work with cluster Poisson coordinates, so we construct cluster Poisson variety. So this any cluster Poisson variety admits a canonical quantization. Well, we define variety chart by chart and then some gluing data. So the quantization will define as well the same way. We'll define quantization chart by chart and then just quantize the gluing data. So as I promised, we will be only quantizing the algebra of functions on this cluster variety. So chi q is a chart labeled by the quiver q, and algebra of functions on a, well, chi q is a c star to some power d. So algebra of functions is just polynomials in variables y1 up to yd and their inverses. And then what we do, we quantize that guy, just replacing it really with what people call quantum torus. This is by definition algebra over rational functions of auxiliary variable q and some variables y1, some generators y1, yd, and their inverses. And the relation will be that yj, yk is equal to q to the 2 epsilon kj, yk, yj. Right. Fine. That's clearly a quantization of log canonical Poisson structure if we take the quasi-classical limit. But let me give it slightly different, slightly better, to my taste, description of this already very simple algebra. So equivalently, we can do the following. Let's choose. So we have, you see, we have d variables. So let's choose a lattice lambda, which will be just z to power d, so just integer lattice, with a bilinear form. And then, well, yeah, with a bilinear form, sorry, on this lattice. And then we define, so you see how over here, our torus depended on the quiver q, which it should have. But now I want to define a torus which completely independent of the quiver, so I'll just define TQ, kind of master torus, which will just by definition be, again, algebra over rational functions of Q, with generators y lambda. This lambda will be an element of the lattice, and relations Q to the form evaluated on pair lambda mu, y lambda y mu is equal to y lambda plus mu. Then indeed, this master torus and these torus, they're related in the following way. So choosing a basis E1 ED in lambda, we get a quantum torus by just saying well, quantum torus with generators y1, yd, where these generators yj is just y epsilon j, so it's just y corresponding to this basis element of our lattice, right? And this epsilon jk is just by definition the value of our bilinear form on ej on the two elements ejk. Right? So really, what I'm saying is that you can just have one master torus, and then different cluster charts is just different choices of basis, right? So in other words, charts are charts come from choices of basis. In particular, it tells us that, well, if you started with some cluster chart and you did some monomial transformation on the basis, which seems completely harmless on the level of chart, and then you start mutating, you did something completely horrible to your cluster variety because you changed basis slightly. Well, just did some monomial transformation. You completely changed the matrix that defined how you will mutate later on. And then you get, when you start mutating, you get a completely different variety. So the cluster variety is not just given by chart, some chart. It's given by chart and a set of functions on this chart. So you need to know the Poisson brackets between these functions. And that's why every question about how A variables and X variables and boost X variables are related, they are all very clearly related. But the cluster story doesn't, well, you cannot just change to loose X variables and start mutating. You will get something completely different. So, right now, what's a quantum mutation? Well, quantum mutation is the following thing, right? It's we needed a birational isomorphism, so we now start with some chart labeled by quiver, and we want to get to another chart, this chart with mutated quiver. But the problem, of course, is that we have to divide by 1 plus x or something like that, so really get into some field of fractions of this guy. And of course, this thing is a non-commutative algebra, but it satisfies, luckily, it satisfies Euler conditions. So we can, well, it's a quantum torus, so we can definitely define the field of fractions, non-commutative field of fractions. So our quantum cluster mutation will indeed hit over here. And the way we're going to define it, we're going to factor it into two things. So we will first define a map indeed from one torus to another. This map will be just, so this, I think people don't know that I'm mu k prime, and this is just change of basis indeed. Change of basis in our lattice. And then there will be another map that's usually denoted mu k sharp. And this is some automorphism of some birational automorphism of the latter torus. So let me describe these two charts, and that will be more or less it, almost. So what's mu k prime? Well, the rule is as follows. So ej just goes to ej prime, if you wish, which is just minus ek if j is equal to k, and ej plus, I'm going to write epsilon kj plus ek if j is not equal to k. So this guy over here, well, yeah, maybe I should, yeah, a plus is equal to a if a is greater than 0, and to 0 if a is less or equal than 0. So this is just taking the positive, well, taking epsilon kj if it's positive and forgetting it if it's negative. So again, example. If you start with a quiver like this, so let's say this is ek, this is ei, and this is ej, and I want to apply mu k sharp. The only thing I'm doing, I'm changing the basis, right? So ek becomes minus ek. then there was an arrow from k to I. So I becomes EI plus EK. And there was no arrow from k to j. So this stays EJ. And as you can see, if you just look at commutation relations, at the bilinear form evaluate on this new basis element, you get precisely the mutation of the quiver that we promised before. So this is the first part. This is the change of basis indeed. And second, the mu k sharp is an automorphism, and this is just, again, by definition, some conjugation by some special function called quantum dilogarithm. So where this psi q of y is the following expression. So it's an infinite product, j greater or equal than 1 over 1 plus q to the power 2j minus 1 y. So let me spell it out. It's 1 plus qy, 1 plus q cubed y, 1 plus q to the 5th y, and so on and so forth. And this is what people call quantum dilogarithm. So this function actually has several names. It's either called quantum dilogarithm, or q exponent, or q gamma function. All of these names, they actually have very precise meaning, but let me kind of show why it should be called a quantum q gamma function, because really you can see that if you shift the parameter, if you write psi q of q square y, what you get is just 1 plus qy times psi q of y. Just because when you shifted y by q square, your product starts at this term, so you're kind of forgetting this 1 plus qy in the denominator. Right? And this is well, if you take a limit in a smart way, you just get the relation for gamma function. Gamma of x plus 1 is x times gamma of x. Now let's see how this works. So let's see an example. So somehow we conjugate by an infinite series, and of course we shouldn't expect to have a birational transformation, but we do precisely because of this equality. So let's just see example. So mu k q of yk. Well, what is it? So this is mu k sharp, so conjugation by this quantum dialog of yk inverse. But we're going to conjugate yk by a function of yk. So obviously nothing happens. So this just stays yk prime. Yk can use with itself. So this is yk inverse. Sorry. Now what's mu k q of y I? Well, this is mu k sharp, so conjugation by quantum dialog of remember it's y and here we have ei plus ek. Y ei plus ek. Well, what is it? Like what mu k sharp is, as we discussed, it's a conjugation by yk. And y ei plus ak, we can decompose it as q inverse yi yk, right? Just because of how we defined over here that, sorry for scrolling, over here we had this relation over torus, right? So we can factor it as q inverse yi yk or q yk yi. Right? So, sorry. And here we do conjugation, and here we do psi q of yk inverse. And when and then let's note that from our relation, from our curve over here, we can see that yi yk equals q square yk yi. So when we'll be moving yk through yi, it will acquire a q to the minus 2. So what we'll get is q inverse yi yk psi q of q to the minus 2 yk psi q of yk inverse. And if we use our q gamma relation, that becomes q inverse of yi yk 1 plus q inverse yk, or if you wish, yi times 1 plus q yk inverse. Anyway, so this form here, if we set q to 1, we exactly recognize, yi yk divided by 1 plus yk. So that's exactly when an arrow was pointing from k to I. This is how things mutate. And finally, the last calculation, mu k q of yj, would be mu k sharp of still yj because nothing happens to this. Oh, sorry, nothing happens to this guy over here. And when we conjugate, you'll see that it's yj times 1 plus qyk. So precisely the needed thing. Now, I realize I'm over time, but I just want to take maybe 3 more minutes and finish the story about quantized Toda Hamiltonians. If
for me, it's okay. Yes.
But yeah, if not, yeah. Sorry. Okay, I'll try to be quick, concise, and right, okay. So now we know what's quantized cluster algebra. So let me just show quantized Toda Hamiltonians. The rule is really simple. So what you do is you take yi1, yid. Remember, these are the classical variables in which we wrote Toda Hamiltonians, right? And what we need to do, we just need to replace those guys by ei1 plus dot 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 plus eid. So this way, I never have to worry about which powers of q I'm going to put in the summand. So for general quantum cluster algebras, this is not as simple. I'm not gonna discuss that now, but in this story for double Bruhat cells, you can just replace this guy by these things. And if you want to write it in e1 y1 yd, you just decompose it, and put it in some order and put some power of q before it. So example, let's do an example. Well, let's do SL2. So our network, or black-white graph, is like that. We have variables x1, x2, x3, x2 points to x1 and x3. So when we wrap it on the cylinder, so when we mod out by the torus, what we get is a quiver like that. So this is y1 and this is y2, and y1 is x1, x3, and y2 is just x2. And then we can, so what's H1? The only non-trivial Hamiltonian would be the trace. So H1, the trace will be just 1 plus x2 plus x1, x2, x3. But remember, if we want to do SL2 case rather than PGL2 case, we need to divide by the square root of the determinant. So we get, if we spell it out, y1, y2 to power minus 1/2. Plus y2 over y1 to power 1/2 plus y1 y2 to power 1/2. And if we want to quantize it, it's really easy. We just take y to power y, well, an element of the, to be honest, half lattice rather than the lattice, but it actually doesn't make anything more complex. It's really same story. E2 minus E1 plus y 1/2 of E1 plus E2. So this is, so really we're using half lattice, or in general would be using lattice kind of 1 over rank G lattice. So we need to allow not integers, but 1 over rank G integers. Now this is all good, but of course it's impossible to recognize, from these formulas, it's impossible to recognize what Toda Hamiltonian, any known formulas for Toda Hamiltonians. Known formulas are something like Q difference operators. So, and for that we need to just take a representation of the quantum cluster variety. And again, I'll just do it by example. So what do we need to write a representation? So we need to, let me do a SL3 case, slightly more informative. So here we have variables y1, y2, y3, y4, and we choose the, let me choose canonical coordinates. Xj and pj, which will be 1 over 2 pi I d over dxj. Then I want to write some parametrization of this cluster variables of y's in such a way that the bracket of yj and yk would be 1 over 2 pi I epsilon jk. And it's, so for example, I can put y2 to be x2 minus x1, and y1 to be p1 minus p2, and y3 to be p2 minus p3, and y4 to be x3 minus x2. Well, indeed, then, for example, the arrow between these two guys, right? The x2 with minus p2 will give me 1 here, and minus x1 with p1 will give me another 1, right? And here there's one arrow because the only non-trivial commutation relation I get from minus p2 and minus x2, so I get the right commutation relations, and then I can set q to be e to the pi I b squared, and set yj to be e to the 2 pi b yj. Then indeed I'll have the relations that yj yk equals q to the 2 epsilon kj yk yj. So as long as I somehow parameterize this kind of the logs of the cluster variables, right? So that they satisfy these conditions. Now I can write. Now my cluster variables become. So what they become? They become multiplication operators by exponent of canonical of sum of xj, right? And they become shift operators. So e to the p, e to the d over dxj, right? And in, for example, so y1 becomes e to the 2 pi b p1 minus p2, and y2 becomes e to the 2 pi b x2 minus x1. Right? Now, what it is in terms of what it is in terms of, so let's just write Toda Hamiltonian for SL2 in these terms. Before I do that, let me actually change slightly my parameterization. So I'll change my parameterization, but the quiver will stay the same, of course. So I'll add plus x1 minus x2. I'll add plus x2 minus x3. You can, so this I'm doing only to recover the standard formulas for Toda Hamiltonians. I could have written it as they were. So here I'll just have p1 minus p2 plus x1 minus x2. And then if I write Toda Hamiltonian for SL2, well, what do I get? I get, so the first term, this guy over here, right? It's minus 1/2 of sum of these two guys. So it's minus 1/2 of p1 minus p2. So I get e to the pi b p2 minus p1 plus another term will be pi b p1 minus p2 plus in last term will be this term here, b to the pi b 2x2 minus 2x1 plus p2 minus p1. And if you want, and maybe it's still a bit hard to recognize, but if you want GL2, you just kind of multiply it all by an overall Casimir, multiplied by Casimir, e to the pi b p1 plus p2. And what you get then is e to the pi b, sorry, e to the 2 pi b p2 plus e to the 2 pi b p1 plus e to the 2 pi b p2 plus x2 minus x1. And this is the formula that I believe, well, at least I've seen it in a bunch of papers. Of course, you can do, you know, so the only thing that really matters, so only thing that matters here, only thing that really matters is that H1 of GL2 is, after all, just a sum of thing that is sum of three terms with the relations that AB equals Q squared BA, CB equals Q to the minus 2 BC, and AC equals CA. But then if you want H1 SL2, you just declare, you just set AC equals 1, right? And then you get A and A inverse, right? But then this is just different parameterization. And the very, okay, very much over time, but the very last statement, I just want to make a claim. So kind of a bonus game just to, so what I've done so far, I explained how to put cluster coordinates, how to quantize them, how to write quantum Toda Hamiltonians from these coordinates, all of this nice, and absolutely no reason to be interested because I haven't explained a single application. So let me explain one application. And classically, this result is due to Gekhtman, Shapiro, and Vainshtein, because there were a whole zoo of different integral systems that people call Toda systems. And they explained classically that all of them is just the same Toda, but just written in different clusters. And then there is a quantum version of that. So then there was a work of Pasha Edinburgh and Alexei Sevastyanov, and lately, Gonin and Cymbaluk and type C and so on, when they write, again, 3 to the rank many different integrable systems, quantum integrable systems, in terms of Flex matrices, and they call them Toda systems. And there's a kind of bonus. It's a result of Corey Lunsford. It's some kind of undergraduate student of mine from Berkeley, fantastic guy. So he explained that this quantum Toda systems from, well, this 3 to the rank -1 quantum Toda systems from works of Ettinghoff and Sevastyanov. Plus Gonin and Cymbaluk. So they really just didn't add anything in type A to that, but did in type C. So they are the same quantum Cockster Toda system. Cockster Toda system written in different charts Q to the I, and they're exactly 3 to the rank -1 different ways to kind of write this double wild word cyclically, right? When we do it, when we put it on the torus, when we put it on the cylinder, it doesn't matter, where we start. So they're exactly 3 to the rank many of those and 3 to the rank many of those, and that's a nice but rather simple combinatorial result. That this is all of the systems are just the same one, but written different clusters. I'm sorry for overtime. Yeah, I'll stop here.
Sash, thank you very much for such interesting and complete talk. But it's not complete, but it's dense. And so thank you very much. If there are some questions, please. I have many questions, but for future discussion.
Thank you. If possible, I would ask one question right away. What kind of transformations do your cluster transformation generate on Hamiltonians, on the Toda Hamiltonians? Is there something meaningful at all?
Well, I mean, you have to define the word meaningful, but what? Right.
I mean, are there closed transformations which your cluster transformation generate on the Hamiltonians?
Should be.
Well, okay, so the cluster transformations, you can apply them to Hamiltonians. You get different sets of Hamiltonians. So you don't preserve the set of Hamiltonians. So just formulaically, your well, for example, the number of terms in the Hamiltonians can change, of course. But I mean, it's not that it's not that you have an algebra and you have an automorphism of the algebra. It's rather you have an algebra and you you have isomorphism between different, like bunch of commutative algebras, right? Now, another thing that cluster transformations can do, and that would make sense in this respect, is they, for example, can generate there's this thing called discrete dynamics on the Toda system, or people call it also discrete Q system and so on. So this is also part of the cluster data. That, of course, again, doesn't do anything to Hamiltonians because they commute, but it's still another part of the story, of the same story, right? Yeah. But again,
sorry, will it be cluster transformation as well? I mean, this transformation which is generated on the Hamiltonians.
Say it again, sorry.
Will it be cluster transformation again? I mean, your cluster transformations will generate some transformations on the Hamiltonians. Will it give you the structure of cluster algebra on the Hamiltonians?
I think we should phrase this somewhat differently, right? So what do we have? We have a cluster variety. We have a variety covered by cluster charts, and we have a set of functions. We have a set of Hamiltonians on this variety. So yeah, and then we can write these Hamiltonians in different charts. And cluster transformations go from one chart to another. So it's not that you have kind of cluster structure on the set of Hamiltonians. You rather have cluster structure, just Poisson, classical Poisson geometry, right? You have cluster structure on the phase space of the system, and then you can write your Hamiltonians in different charts. And when you write them in different charts and quantize that, you precisely get this 3 to the rank many different Hamiltonians, 3 to the rank many different ways to write the same function on the same space or in the same representation. But now, kind of, well, in representation theory level, what you get is you just get unitary equivalences between. So on the representation theory, you get you will not have a variety, but rather non-commutative algebra. You'll have a representation of this algebra, and for each chart, you'll have a separate representation. And then your Hamiltonians will act differently in these representations. But cluster mutations will give you unitary equivalences between these representations. Mm-hmm. And on top of that, you'll have an action of this discrete transformation, which will preserve the Hamiltonians. Mm-hmm. It will just commute with Hamiltonians.
May I ask a short question? Maybe not very much directly related to your talks, but maybe it does. You know, in integrable systems, we have such a phenomenon like multi-Hamiltonian structure. That means the same equation may have different but compatible Poisson structures, and the same can be promoted to the quantum level. So you may have different quantization to the same system. You have, you know, the system is the same. The commutation rules or Poisson brackets are different, you know, and you have also the hierarchy of Hamiltonians. Maybe you heard about Leonard scheme or things like that. And that exists for everything, for Toda lattice, for Volterra lattice, for KdV equation, for finite dimensional dynamical systems. I wonder what reflection of this picture is in your cluster construction.
Yeah, it's a very good question. The thing about clusters is that so clusters don't see that, and for a very good reason. The clusters, it's a story about log canonical coordinates. So your Poisson bracket has to be quadratic. So with the Toda system, right, you have two brackets. You have a linear bracket and quadratic bracket, and they're the two compatible brackets, right? And then indeed, if you kind of have two in mind, you can iteratively construct Hamiltonians and so on. The linear bracket, the cluster combinatorics, these mutations, so on, they only work well with quadratic brackets. So that doesn't appear, unfortunately.
Well, you can make a different change of variables for different, you know, Hamiltonian structure to come back to, you know, log whatever brackets, you know, to quadratic brackets. That's what I think, because you know,
no, go on,
you will have in different variables, but there's the same system.
Right. So right. Let me correct myself. So you can do that, of course, but for that you will have to make a non-algebraic change of variables. Now, the one kind of simple but very, very nice result about log canonical brackets is the following: that imagine that you have a Poisson variety, and you have some coordinates that have log canonical brackets, and you can ask, are there any algebraic transformations, that algebraic changes of variables that allow you to make these brackets maybe linear or maybe constant, something like that? And the answer is no, you cannot. So if you already have log canonical brackets and you only allow algebraic transformations, then cluster variables is just the best thing you can hope for. So it's a replacement for canonical variables whenever you cannot have them. So when you exponentiate, when you do this non-algebraic changes,
I understand. I understand it perfectly. Now that what you want to say is that your cluster picture means such important phenomena as multi-Hamiltonian structure, right?
Yeah. I don't know any reasonable way in which you can see the well, when you can see different brackets and on the same system from cluster point of view. Things that you can see though are things like the bispectral property for Toda. You know, how on the same phase space you can see, you know, Todas.
One example maybe exactly would fit your structure, but not multi-Hamiltonian, but also puzzle me. Look, recently I kind of devise a new approach to quantization, and I found two different quantization for the symmetry of Volterra chain. But Volterra is not far from Toda, you know, that basically they're relatives. So if you take not Volterra, but a cubic Volterra, the symmetry of Volterra, it admits two quantizations, and two quantization in your sense that you have a product of two, operators on sides, and if you swap the position, you multiply, you have some multiplier, right? Which depends on the positions. And one quantization is standard, like people use, you know, like Fadeev, School, Volkov, etc., use for, and which goes directly to Toda if you do change of variables to Toda. And another is a new, and is not even a deformation of, you know, a classical structure. I really would be interested to see if can you go bypassing the classical theory, I mean, you have, if you start from Poisson structure, right? From Poisson brackets, Poisson structure, log Poisson, I mean, the canonical log Poisson. And then you arrive to these quantum homogeneous structures, right? Can you work directly from quantum homogeneous structure and go back to log Poisson?
No, of course, but I mean, this direction is easy, right? You just take the quasi-classical limit. This of course you can do.
Quasi-classical limit, if you can take, if it's deformation, if it's a deformation of plastic.
It's already not a deformation.
If it's not a deformation.
Yeah, that no. I mean, this cluster story, at least as far as I know, all the examples that I've seen, it works in the most natural setup when it is a deformation of some Poisson variety, and the brackets are quadratic. Any other, other situations, I don't think I haven't seen any works about that.
Okay, maybe we can talk later. Okay, thank you.
Yeah, absolutely. Yeah, sorry.
But it's a very good question from Sasha Mikhailov.
Yeah, it is. Yeah.
Very good question. Sash, but am I right that your quantization in cluster variables correspond to the quantum group, which is a quantization of the Poisson-Lie group?
Yes.
Okay.
Yes. So indeed, when you quantize the double Bruhat cells, right? What you get is indeed just well, I guess. So Poisson manifolds correspond to what to modeling out by ideals. But anyway, that's quantization that's the quantization of. So if you take the big Bruhat cell, right, that would be directly the quantization of algebraic functions on the group with the standard Poisson structure. Yes. So in a sense it's not related to quantum group, but rather to the Hopf dual of the quantum group.
Okay. I think that we should stop. So I'd like to thank all the participants. We continue in 2 weeks. Sasha, could you stay for some minutes? Thank you all.
Which Sasha, me or him?
Саша Шапиро, Саша Михайлов, ну, тоже, конечно, если интересно.
It's okay. See you soon.
See you. Ну, мне бы хотелось какую-нибудь дату просто назначить, чтобы мы поговорили об этом конкретно, потому что я очень много нового материала для себя узнал сегодня. Саша, когда вам удобно?
У меня, наверное... Не, ну у меня в общем свободный график. Наверное,
какой-нибудь четверг утро, вот не получается такое?
Дайте я посмотрю.
Ну, не завтра, а там,
да, я понимаю, сейчас.
Наверное, через 2 недели, вот что-нибудь такое.
Секундочку.
Например, 14 октября.
Да, 14, наверное, хорошо, да.
И прям с утра, ну вот по Москве, если с 10 до 12.
Да, отлично.
Отлично. Давайте тогда вот такую дату будем иметь в виду, а ближе к делу.
Хорошо, да, отлично. Давайте.
Вот, честно говоря, мне кажется, что можно еще раз, в смысле, еще доклад вот на этом семинаре, но там через пару месяцев.
Да,
После того, как мы еще поговорим, я просто думаю, что мои вопросы будут точнее, и тогда и вам будет интереснее. Ну, мне сегодня было очень интересно, то есть прям здорово, и спасибо огромное.
Спасибо, да, я прошу прощения, что долго получилось.
Ну, мы потеряли многих людей, но мне было все время интересно.
Хорошо, ладно.
Еще раз спасибо, Саша. Вы можете прислать, значит, доски?
Да, конечно. Да.
Ага. Еще раз спасибо, хорошего вечера и до 14.
И вам, да.
Счастливо.
До свидания.